Hello guys, nice to see you.
Hi.
Hi.
Hello.
Good afternoon.
Hi.
Hello.
Hello.
Hello everyone.
Hello.
Good afternoon.
Good
Good
afternoon.
afternoon.
Hello.
Good afternoon.
Hi.
Hello.
So, how life is going? Everything is fine?
Good afternoon.
Yeah, sure.
Hi. That's
Yes,
good.
fine.
Good afternoon.
Hello.
Good afternoon.
Okay. So, maybe a short reminder of our previous discussion when we introduced units and dimensions. So, who can remind me what is the main meaning of dimension? What does it provide to a quantity?
A fundamental characteristic.
Yeah, it provides physical meaning to the quantity. Otherwise, it's just a number, and once it has some dimension, it already a physical quantity. And then we can compare physical quantities. They should be with the same dimensions if we compare them. And physical quantity can be measured with plenty of different units. So it's meters, centimeters, inches, foots, but in all these cases, it has the same dimension, means the same physical meaning, its length. Also we consider that it's very important to carry out dimensional analysis when you derive your equations when solving problems or working on some research projects, so you avoid possible mistakes. And another neat feature of this dimensional analysis is to predict certain dependencies of physical processes or estimate physical quantities based on dimensional analysis when there is no developed model for this particular physical process, but you want to estimate within the error of some constant. You can do this in many cases with simple dimensional analysis. What can be quite useful, and in general, it looks quite nice when you do something like this. So if you have any questions on the way, you're welcome to interrupt me and ask.
Sorry, Viktor, I have a question.
Yeah, sure.
So we will have theory questions on our exams?
No, this online teaching process is organized in that way that you have for all your exam, midterms and final exam, only problems to solve in LongCap.
Okay, thank you.
Yeah, but keep in mind that in order to solve problems, you need to know theory. And another important thing for future, since like within this course, you will be technically evaluated by your skills to solve problems. But in future, definitely it will be necessary for you to express your point of view, your understanding of certain scientific questions, including those related to physics, in a clear and short form when you communicate with people or present your results or answer questions during your presentations. So this is also very important, and it's one thing to know the theory and understand the concepts, and it could be very different from ability to explain this in to some audience yourself. So that should be something where you should practice. And I believe that asking questions, that's also another possibility to practice with this, because questions about physics, they also should be formulated properly. So when you ask these questions, you also practice. There's a question if we can do some practice with dimensional analysis. I believe that we cannot really focus too much on this, I would say, introductory topics. I guess we had few examples considered yesterday. If you missed that, I mean, not yesterday, last discussion, if you missed that online discussion, it is recorded and available online. And for sure, in the textbook, you can find some other examples which can be considered. So I believe it's not such a difficult and for understanding topic that we can afford to focus for too long. For instance, today we have another kind of introductory topic, which maybe most of you are quite familiar with. However, there is a chance that you will learn something new, and even repeating it is very important, because we need all to be in the same starting point when we proceed further with considering physics concepts within our course. Of course, vectors, which are going to be the topic of our discussion today, is one of the very important component of dealing with physics concepts and physics problems within course of mechanics, for instance. Not only mechanics, but that's what we take care right now about. So for sure, I would prefer to proceed now with vectors and like introduce vectors, explain some main mathematical operations which you can do with vectors, because that is quite important, and you will deal with this very often.
Sorry, teacher, can I ask a question
Yeah.
about long kappa?
Yes, sure.
Will we have a link, and what about ex-founders? Should they use their old account that was used during foundation year?
Oh, that's a good question. I believe that it can be properly addressed by our long kappa administrator. Please email him, Azamat. His contacts are in this manual file. It's a bit tricky moment, because not, as I understand, not every one of you guys were in this foundation. So some of you just came here for the first time, and maybe in order to avoid any misunderstanding, maybe you will have new accounts, but that is my guess. Of course, our long kappa administrator, he is responsible for creating these accounts, and he definitely knows better how properly it should be organized.
Okay, thank you.
You're welcome. Okay, guys, so we a bit mentioned about this before, but there are two types of quantities, like physical quantities, scalar and vector. So scalar is, like, for instance, temperature. It's enough to provide some number which defines the temperature, and that's all. So some scalar number is sufficient to describe this physical quantity. However, it's not true for many cases. For instance, let us consider such similar things as speed and velocity. So speed is scalar number, defines how fast body moves. and that's all. It doesn't have any information on the direction of this motion. However, speed is already a vector, and it is more interesting because it has this every vector, like some speed vector, let's say, but it's also true for any vector. It has both amplitude and direction. So amplitude of speed, it is technically, sorry, not of speed, of velocity. Amplitude of velocity is technically speed because it just shows how fast this body moves. However, in addition to this information, it shows us also in which direction this motion is happening. So this is definitely more informative, and it brings not only additional features, but also a bit more complicated analysis and quantitative operations with such physical quantities, which provide information on amplitude and direction. So let me change my camera so you can see. Here it is. Before we go to vectors, since vectors usually need to be defined in some multi-dimensional space, so we go for the most simple case. It's 2 dimensions. We are not enemies to ourselves to make our life too difficult. Let us introduce a system of coordinates with 2 axes. Axis X, axis Y. Could you please switch off your microphone? Guys, please don't make background noise. Switch off your microphones. If you want to ask questions, then turn it on. So we have system of coordinates, and let's say there is some point. Do you hear me, guys? Please switch off your microphones, everyone. So how can we define, so there are 2 most common system of coordinates which we are going to cover. So it's a right angle system of coordinates, which is shown here. We have X and Y axis, and there is polar system of coordinates. So in right angle system of coordinates, this point can be defined by the position, like the coordinates X and Y. So if we know X and Y, we easily can identify the position of this point in space, in the 2-dimensional space. However, there is another option to deal with this, is to use polar system of coordinates. And in this case, we have radius r and angle, let's say theta. So there is a relationship between polar and right angle system of coordinates, like position coordinates and radius and theta. And this comes from the fact that here we deal with a right angle triangle. Let's say A, B, C is right angle triangle. Who is making this noise? Can you tell me, please? Cannot identify, unfortunately. Okay, sounds better now. But please be aware that I understand that maybe you forget, but before you start this discussion, please switch off your microphones just to be sure that it's not interfering with our work. But don't keep it always muted, so don't forget to ask questions. So, please excuse me. Now I have some background noise. So the relationship between r and theta and positions like coordinates x and y come out from this right triangular. So we can write that x is equal to radius r times cosinus theta. Y in its turn is equal to radius times sinus theta. So that is the relationship between these two. Also, if we want to define alpha, this angle theta, tangent of angle theta is equal to the ratio between y and x coordinate of the point. And also from the right angle triangular, we see that here radius serves as hypotenuse of this triangular, and that's why we can calculate it as square root of the sum of x squared plus y squared. So this is a general introduction of systems of coordinates we mostly will work with, within which, in the frame of which we will deal with vectors. So let's say we have point A and point B. And there is some motion of some body from point A to point B with such curved path. So the length of this curved line will be called path of the body while moving from point A to point B. So this path is a scalar quantity because it just defined the length of this curved line, which is trajectory of the body. However, there is another parameter, which is displacement. And that is a vector which originates at point A and ends at point B. And this vector, like displacement, provides information on the direction. And so it has some amplitude, which is the distance, shortest distance between A and B, and direction, which is along the line which connects these 2 points. So its displacement is defined only by initial and final position of the body. And path, it can be anything, depends on the trajectory. So here we have clear example of difference between scalar and vector quantities, which are at the same time quite close in nature to each other. So now let us consider how to do some operations with vectors. Obviously, if we have different vectors, we need to do something with them, what is necessary for in the scope of our problem. So most common is to add vectors. So let's say we have vector A and we have some vector B. So let us arrange vector B in that way that its origin starts at the end of vector A. So now under this arrangement, we can show that vector C is actually the sum of vector A and B. So we can write vector C is equal to vector A plus vector B. So what if we have more vectors? So they actually follow the same rule. So we have vector A, vector B, vector C, and vector D. So all of them arranged in that way that the origin of next vector is located at the end of the previous one, and the resultant sum vector, let's say E, will be also defined by connecting the origin of the first vector and the end of the last vector. So with this, it is kind of clear. However, let us consider one more feature. In particular, if we rearrange this first figure a bit, for instance, we transfer this vector B here. So this is vector B. And vector A, we will arrange its origin at the end of vector B, something like this. Not ideal, but okay. So this is vector A. And you see from this figure that the sum of vector A plus B is equal to the sum of vector B plus A. So that is it doesn't matter what we will add first, the result will be the same. So now let us introduce negative vector.
Professor, excuse me, I have
Yes.
a question.
Mm-hmm.
In school, I was taught that when we define vector, when we give name to vector, we should use either one small letter like small a or small b, or we should use two big letters. So are you saying that in English language we can use capital letters for naming the vector?
Yeah, I think it's not so strictly defined. You just need to be consistent in terms of putting errors on top. So it is highlighted that this is vector, and how you call it, that is up to you. It's not so critical. So definitely you can stick to some rules, but for instance, here we will use these capital letters for vectors. It's okay.
Okay, thank you very much.
It's not so critical. Introducing negative vector. So let's say we have vector A, and negative vector A minus A will be the same vector in amplitude, but in opposite direction. So this is minus A vector. So in this case, when we have this negative vector, we can start to subtract vectors from each other, applying rules of adding vectors. So how does it work? Let's say we have vector A and we want to subtract vector B from vector A. So that is equal to vector A plus vector minus B. So if we convert vector to B to vector minus B, then if we add this vector to vector A, we will get the answer to this subtraction. Another important feature which you guys should remember, it is multiplying vectors by scalar numbers. So let's say we have vector A again, and we want to multiply this vector by 2, 2 times vector A. So that will be the same vector, so the total vector will be equal in amplitude to 2 vectors A, and the direction will be the same as direction of vector A. So it can be written as 2 times A, it can be written as A vector plus A vector. So now we need to introduce unit vectors. Unit vectors, they are very useful because it helps us to simplify our life in dealing with vectors quantitatively. You will understand this in a second later why, but now we just introduce unit vector. So unit vector, let's say I, is some vector which defines the direction. So obviously, if it's a vector, it has some direction, but its amplitude is equal to unity. So now we can create any vector we want. We just set some unit vector I. It gives us direction, so it's kind of responsible for direction. And then let's say we have some scalar number A. It's not vector, it's just scalar number. So as a result, we get some vector, let's say B. So the amplitude of vector B, in this case, will be equal to scalar number A. And in terms of direction, this vector B will be in the same direction as vector I. So let us go to another slide and show why introducing these unit vectors can be very useful for us in future to work with vectors. So again, our multi-dimensional space, which is two-dimensional, X and Y. Let's say we have in this system of coordinates some vector A. Now, what we can do. So this vector is randomly oriented in space. We can define its position with respect to this system of coordinates with angle theta. And it is kind of not convenient to work with vectors which are oriented randomly. We want to get some real vector, which is randomly oriented, and then convert it to some system which will be convenient to work with. And in this particular case, there is only one way to go. We want to split this vector A in two vectors, which will be aligned along axis X and Y. So that will help us a lot because then it will be, we will deal with components of vector AX and AY, and it will be much easier later to add or multiply two vectors in future. So let us get these projections. The projection of vector A is AX, and keep in mind we don't put vector here because this is scalar. It's just projection on axis X. And here we will have AY. So this is projection of vector A on axis Y. Now we add here unit vectors. So this is unit vector I, amplitude unity, and direction along axis X. And here we add unit vector j. The same amplitude unity, but this one is vector j. Unit vector j is aligned along axis y. So now we can represent vector A as the sum of two vectors. First vector is ax scalar number, which is defined by the projection of vector A on axis x, times unit vector I. So now we have, let's draw it here. So this is vector ax times I, and this will be vector ay times j. So plus ay times j. So now we can split this vector in two components. Looks like we make this system, like this case, a bit more complicated because we had one vector, now we have two vectors. But it's better to deal with two good guys than with one bad. And now we will show why we want to do this. So let's say we want to add two vectors. This part, we have again system of coordinates, x, y, and vector A and vector B. Each of these vectors can be projected on axis x and axis y. So we will have ax, then bx, all this will be bx, this will be ax. Then here will be ay, and here will be by. So now when we want to add them, we don't...
Excuse me, you made a little mistake. I guess bx should be the one smaller.
Oh yeah, you are right. Thank you very much. You are right. So it's bx, and this longer one will be ax. Thank you. So now we want to add these vectors, and how can we do it? We don't need to think about moving vector b, its origin, to the end of vector A, and then connect origin of vector A with the end of vector B. Instead, we deal with this splitting both vectors in their components parallel to axis x and y, and then literally just add them. So for vector B, we can write the same. So it will be, it will be bx times I plus by times j. And now, in order to get the sum, it will be some vector c. The vector c is equal to I times the sum of projections of vector A and B to axis x. It will be ax plus bx. And then we have plus another component of this resultant sum vector, unit vector j, times the sum of projections of vector A and B on axis y. So ay times by. Okay, so you see it's very clear and intuitive option to do these calculations with vectors. Now, usually we will consider multi-dimensional spaces in terms of system of coordinates with two axes. So it will be two-dimensional space because it is the key transition between one-dimensional case to two-dimensional case when you introduce actually vectors. That will be clearly shown when we consider next week motion along straight line in one-dimensional case and also motion in two-dimensional cases. However, going from two-dimensional to three-dimensional is kind of trivial. It already doesn't make such a fundamental difference. However, let us also consider in that case to make it more general description. So let's say we have system of coordinates with three axes, which is x, y, and z. So if we define some vector a in this system of coordinates, so we obviously have, maybe let's move it, vector a. We have projection of this vector on each of the axes. And this will be a z, a y, and a x. Again, we want to split, to represent this vector a as a sum now of three vectors. So it will be here unit vector I, here unit
sorry, sir.
J, yes.
Shouldn't we use the right-handed the system, right-handed coordinate system?
Yeah, but we can use any system we want. It's just some general example. We are
okay.
strictly limited to some exact cases. So this is this orientation of axis. We can use other, but it doesn't make the difference in understanding the concept. So let's say, yeah, I just wanted to draw this one. We can draw another, but it will not change the understanding of this case. So we have three unit vectors and three projections of our vector A on each of axes. And now we can write that A x times I plus A y times J plus A z times A. Okay, so this is the kind of similar concept as before for two-dimensional, but we just wanted to show it for three-dimensional case to have it clearly specified in our discussion. But in future, most of the cases for our multi-dimensional space, we will use two. It's just easier to not so bulky writing and brings the same concept also in full extent. Now, let us maybe continue with this three-dimensional case and introduce in general some general explanation of two options to multiply vectors between each other. So what kind of products of vectors do you know, guys? There are two of them.
Dot and cross.
dot and cross. Good. So let's start with dot. Can you give us some good example of application of this dot product in physics, in mechanics in particular? So what is the result of dot product of two vectors? Is it
A scalar?
a scalar? No. That's important moment. So when we have dot product of two vectors, we get a scalar. If we have cross product of two vectors, we get another vector, which is aligned perpendicularly to the plane where first two vectors are oriented, aligned. So let's come back to the dot product. So we have two vectors, multiply them and get a scalar. So one of the best examples, I believe, is when we consider some force exerted to a body and displacement of this body. So we have two vectors, we have force vector and displacement also vector. And we want to find work done by this force, which caused this displacement. So in this case, we need to have a dot product between force vector and displacement vector. Eventually, we will get work done by the force, and this work is scalar, scalar number. Work is not vector. So this is one of the good examples of application for this dot product. So let us write, let's say we have again two vectors. It is vector A, so AX times unit vector I plus AYJ plus AZK. Then vector B, BXI plus BYJ plus BZK. So we want to have this scalar or dot product of two vectors A times vector B. So as we already mentioned, this will not be a vector, it will be a scalar. And this quantity of this scalar will be defined as follows. It will be AX times BX plus AY times BY plus AZ times BZ. And if we consider amplitude value, amplitude value matters only for cross product. So that will be just a scalar number, which is equal to, can present it in another form. It will be A vector absolute value times B vector absolute value. So it actually length of these vectors times cosinus alpha. Alpha is the angle between these two vectors, A and B. So this is about scalar product, and I think quite clear and simple here. A bit trickier is cross product or vector product. So that is usually shown in such square brackets. Let's say we want to have a cross product of two vectors, A and B. And this is convenient to represent in a form of a matrix, like this product of two, cross product of two vectors. So this matrix will have 9 components. It's unit vector I, unit vector J, and unit vector K. And then here we have AX, AY, AZ. And the same for vector B, BX, BY, BZ. So the as we mentioned before, cross product results in a vector and means that this vector should be defined in the form of projections to each of the three axes of our system of coordinates. And the way how we can get it, we consider this matrix. So let's start from axis X, then we have unit vector I times, and in this case, we consider these two columns. So these elements of the matrix are important for axis X. So we have first diagonal top left times top bottom right. It will be A Y times B Z minus second diagonal, which is top right times bottom left, A Z times B Y. So this is the X component of the resultant vector, which we get because of cross product of vector A and B. Then we need to define in similar way the other components of this vector along axis Y and axis Z. So this is J vector, unit vector. So in this case, we will consider these four elements. So first diagonal AX times BZ.
Sorry, Professor, but isn't there the minus before J?
Okay. BZ, yeah. Sure. Oops. That's, yeah, minus BX, BZ. Thank you. And minus what else? Second diagonal is AZ times BX. So next one we have plus K unit vector, and we consider now these four elements. So it will be AX times BY and minus AY times BX. Yeah, so these are components of the resultant vector, which is the result of products, cross product of vectors A and B. And we can, with the help of these unit vectors A, G, and K, easily operate with such mathematical tasks to find products, add two different vectors, and so on. So it's really helpful, and this is the way how operations on vectors is carried out. Okay, so pretty much everything what I wanted to tell you today about vectors. I think that this is more kind of repetition, recalling your familiar information which you learned somewhere in school probably, or on this Foundry. However, as I mentioned before, we need to be at the same point, and it's good to refresh it before we proceed further with some discussions of physics concepts which involves these vectors and operations on them. So thank you very much for attention. I appreciate your attendance and wish you good end of the week and relax during weekend. So with new energy, come to our meeting on Monday. Thank you.
Thank you. Goodbye.
Thank you, sir.
Thank you.
Bye.
Bye.
Thank you.
Bye.
Bye-bye.
Thank you.
Thank you so much. Goodbye.
Thank you.
Sir, I have a question, please.
Oh, okay, sure.
Will you upload the recording lecture to somewhere?
Yeah, it will be available with that link, which is in the welcome letter.
Okay, thank you.
Mhm.
Bye-bye.
Yeah, you're welcome. Bye.